Right, in this chapter, we're going to talk about motion instructions and the different types of motion instructions that we can do with the robot. So we'll be looking at different motion types, elements of motion instructions, position registers, and how that relates with and how robot speed can affect our motion types, termination types, different motion options, how to add and delete motion instructions within the program, and using predefined positions, again tying to the position register. So in a program we have a motion instruction, and that motion instruction has several different components to that instruction. The first being the motion type, which can either be a joint, linear, or circular motion type. We also have a positional identifier. This position can either refer to a local position, or what we'll learn later on in this chapter is a position register, which can be used globally. That will have a numeric identifier associated with it. And then we also have the percentage of speed of the robot, its termination type, whether that's fine or continuous, and then we have other options that can be added on to the end, be it offsets or some kind of output function, an acceleration callout like what is shown here. And so that's very program specific or motion specific to what we're trying to do. So let's look at the different motion types that are available. So two that are often used are a joint motion and a linear motion. As shown here, the joint motion takes the point at which the robot is at and looks at the target position, and it turns on all the motors simultaneously to start and stop both at the beginning point and at the target position. The motors will all turn at a rate that matches the slowest axis to get to that desired position. So the robot during a joint motion can be somewhat unpredictable in terms of the path that it will follow in getting to that target position. A linear motion is able to go from the current point to its target position in a linear path. So it engages the motors in concert with one another so that it's able to maintain that constant path, that linear path at a constant speed. So again, the pathway is very predictable. And the motors, again, are working in concert with one another to be able to drive that path or maintain that path. As an illustration of the joint versus linear paths, let me show you just a simple program that traces a triangular shape on the board, one using a joint path and the other one using a linear path. So if I go up here to my cycle start, first, it's going to do a joint path between the 3 points, again returning back to its starting position, and then it'll repeat it using the linear path. And watch the direction of the end of arm tool as it traces its line out on this board. Okay, so first our joint path. You can see in this bottom one, instead of doing a straight line across, it looped way down here as the joints all engaged in order to make that transitional point from this point 3 back to point 1. In addition to joint and linear motion, we also have a circular motion that, just like the name suggests, creates an arc between a beginning point and following through an intermediate point and then ending at an end point. So in looking at the circular position, we have a couple of different components that make up a circular path or an arced path. So we have our starting point given here in this diagram that then has an intermediate position as well as a destination position. Using those 3 points, the robot is able to create an arc that passes through all 3 points. Now you'll notice that our intermediate position and our destination position are really part of the same line of code. So the robot recognizes that as a circular path, that one is the intermediate, the other being the destination. Now to create a full circle, we would also need to create another intermediate position and destination position, where it uses the previous destination position of the previous arc instruction as the starting point for the next arc instruction. So both of them can be combined as one being the starting position for the other and then ending back at our beginning position. So with each motion instruction on our program, anytime that we are at the point or that position indicated, we get a little @ symbol. Whether or not that it's the active line of code that we are executing, or if that position happens to be in some other line of code or repeated in another line of code, it'll also show the @ symbol if we're at that position. So when modifying an existing program and touching up points, if that particular position is repeated elsewhere in the program and we're touching up one of those positions, we'll get a comment here at the bottom that will ask us if we want to set a new ID. And what it's asking is, do we want this to be a unique position, or are we modifying that position that's also repeated elsewhere? And it's a good way to double check that to understand what changes we are making and how that could potentially affect the program. Also, take two. Also, with our motion instructions, we can name those particular positions, which can be very helpful in navigating through a program to understand what the different positions, how they may relate to our physical environment. So like here we have a position 1 that was named as a start position. So a person navigating through the program would be able to identify that as a particular starting point in terms of the robot positioning. To do that, we would cursor over that position, the P1, and then we would press the Enter key, and then that would bring up a dialog similar to naming a program or some of the other text functions that we've had. Go ahead and type in a comment, and that would rename that position or leave that comment with that position. Right here I want to talk about some of the information that we have about each of the positional points in our program. So if we were able to pull up the detail, the position detail up for that particular position, we'd notice a couple of things. Here at the top, we would have both that position identifier as well as the user frame and user tool in which that position was taught. We'd also have over here the configuration of the robot in reaching that point. And I'll cover that here in just a little bit, but that's going to be an important thing to understand and note is this configuration change, and especially if we were changing out of that configuration going from one point to another. Here is the coordinate information for that particular point, relative again for the user frame and user tool. So you can see here it's got an X, Y, and Z that is labeled in millimeters, so it's a distance, as well as the W, P, and R. So we've got roll, or yaw, pitch, and roll, both identified as angular position relative to the user frame. So let's talk about the risk configuration for a robot in reaching a point that's identified in its positional detail. So up here we've got an alphabetic identifier that's identifying different components of that robot as well as its turn number. To illustrate the different robot configurations, I'm going to just run through a quick RoboGuide simulation illustrating the three different types, the flip versus non-flip, up versus down, and front and back. So first we're going to look at the non-flip and flip. Currently the robot, let's change it back here to its home position. Okay, so this orientation is the no-flip orientation, as compared to a flip orientation, which is really just joint 5 being transitioned so that the robot is now underneath the point. And now let's go back to our home position, and now we're going to look at the up and down position, which is generally point 3 or joint 3. So without really exercising joint 5, which we could, so that the whole thing would be underneath, we just did with joint 3 and joint 5 in the same orientation that it was with the previous point. So we're just looking at the up versus down, where right now it's in the down orientation. Okay, now let's go back to our home position. And now we'll do the front versus back, where this would be the front, and then flipping the J1 180 degrees and orienting the robot in a back position. It's still able to get, well, in this case, pretty close to the same point. It actually can't reach that point. It's the limitation of the robot, but got pretty close to the same point in a back orientation. So one important thing to note about a wrist configuration or joint placement configuration is that when moving from one position to another that requires a configuration change, we can't do that with a linear motion type. It has to be done with a joint motion type. And so if you ever run into that issue where it says it's requiring a configuration change in going between 2 points, one way to solve that is to change the motion type to a joint motion type, in which then it can make that motion through there. Okay. So one thing that I want to introduce is the concept of a position register. So a register is just a stored numeric value that isn't just a 1 or a 0, but can be like an integer. A position register is where it saves the positional information to a register that includes the X, Y, and Z, W, P, R, as well as the configuration of the wrist of the robot. So a positional point is one that is only locally available in a program. So we define that in a program, but we can reuse that positional point elsewhere in another program with different values, and it won't overwrite that position in whatever other program where we were using it. So it's only a local variable, a locally used variable. However, a positional register is one that is globally accessible. So we can use that we can access that and the information in that position register from any program. So a position register we can use to have a globally accessible positional information. And to access that, we would select data from our teach pendant, and that would often bring us to our data register screen. By selecting F1 for type, we can then pick position registers, and then that will take us to our position register screen. To record a position, you'll notice here one is an R, that means it's got recorded information. One with an asterisk means it does not have recorded information. So we can highlight over the position register we want to use, move the robot to the position we want to teach, and then hit select Shift and record to record that position information under that register. It's important to note that PR's position registers use whatever user frame and user tool are currently active, meaning it takes whatever information, positional information, is inside that position registers and then applies it to the current user frame and user tool that is active. So whatever position we're hoping to go to as a part of that position register may not be the position it goes to if we're using a user frame and user tool that are very different from what was used to teach that position register. So from the position register screen, we can highlight the position that position register that we want to get more information about, and then select this F4 key or position key, and then that'll bring up all the information for positional information of that robot. That'll bring up the position register information in either a coordinate form or Cartesian form, or in an angular position form of each joint. So we can edit that information if we want to make a change to the top position and directly enter in the modified coordinate or position. So depending on how we want that information represented, here under the represent key, we can select either to have it as shown as a Cartesian, or we can have it shown as a joint representation. So when wanting to use a position register within a program, we teach a point and then we highlight over that position or that position, and then selecting the choice key gives us the option of keeping that as a position or changing it to a position register. Once we change it to a position register, within the brackets, we are able to enter in a numeric value, or we can do it with what's called indirect. Indirect means that we can point it to another register. So we could have a register value in here, and then whatever numeric value that's within that register becomes the position register number that the program is going to. And now we're going to spend a little bit more time talking about termination types of a program. So we have two options that define how what the robot is going to do once it gets to the position defined in that motion statement. So we have fine, which means that the robot will stop at the destination point, hesitate before moving on. Or we have a continuous, which means that the robot is going to come close to the point, and depending on how we define it, it'll either slow down or it'll get as close as it can without slowing down before moving on to the next destination. So let's look at what a fine termination type looks like. So here we have a robot that's got three top points, P1, P2, and P3. And moving from to P1, it does that in a joint move, and then it's moving linearly from P1 to P2 and from P2 to P3, all ending at a fine termination. So as the robot moves from P1 to P2, it pauses there, it comes to a stop at P2, and then advances on to P3. So now let's look at what happens with the robot if we use a continuous termination type of motion instruction. So here we have P1, P2, and P3, just as in this previous example. And if we have a continuous of 0, that is just like a fine instruction where the robot will come to a stop at P2. However, if we do a continuous of 100, the robot maintains its declared speed of 2,000 millimeters per second as it gets as close to the point as it can without having to slow down or without having to decelerate from that speed as it moves on to point 3. So you can see how it does a rounded motion that does somewhat like a flyby of P2. If we did something that was more of a continuous 75, it slows down to 75% of the speed as it makes this motion by point 2 and continues on to point 3. Again, and if we do one at 50, again it gets even closer, and so on and so forth. Now let's look at what the velocity looks like for each of those points. So in continuous of 100, the velocity the robot accelerates till it reaches its velocity, and it's able to maintain that velocity of 2,000 millimeters per second, like was defined in the motion statement, as it advances from P1, goes by P2, and down to P3. However, if we do something at continuous 75, as it gets close to P2, it does start to decelerate so that it can get closer to P2 before passing by it and then accelerating back up to its defined velocity. And again, even if we do a continuous of 50, it's able to get a little bit closer to P2 by decelerating even further, so slowing down to 1,000 millimeters per second or 50% of its defined speed before advancing on. So that path can depend on what kind of orientation of those points, or the orientation of those points in the robot path. You can see here in this example, it's able to get pretty close to P2 because the angle in transitioning from P1 onto P3 is pretty large. Whereas in this example, it had to slow down, or the path took it further away from P2 because the angle was a little bit smaller than this example over here. In this example, it's even further away from P2 as a result of the much smaller angle between P1 P2 and P3. Okay, so here we look at a couple of different options and how that continuous move would look depending on what we adjust in terms of speed or in the percentage used in the continuous function. So in this first one, we have P1, or the robot moving from P1 to P2 and then to P3. And it has generally the same motion path, whether it does 2,000 millimeters per second at a continuous of 60%, or if it's slowed down at 1,200 millimeters per second, which would be 60% of 2,000, and then does a continuous of 100% in going around that corner. So the motion path would be very similar. However, they won't be identical, and I'll show you that in an example on RoboGuide. In this example here, we have another way of avoiding this object by including a P4, so it kind of creates a trapezoidal shape, and as it goes around to P4, we do a continuous move between P4 and P2, and then back to P3 as a fine move. Here we're able to maintain 100% of the speed by, again, just elongating this P2 out further away from the object. And so the robot's able to maintain its normal speed by breaking away from this trajectory a little bit earlier, rounding over, and then back to P3. Now we're going to look at some different termination types of our motion instructions as other elements of a motion instruction. So here we have a motion instruction with an additional set of instructions on the end. This offset of a position register allows the robot to offset this particular position at its destination by whatever values are inside this position register. And this gets utilized quite a bit, where we can manipulate the information in this position register and then allow that to offset a particular position, either incrementally as we loop through the program or just as a one-time for some other logical reason that we can put into the program. All right, now let's look at the robot frames and how those are linked in our motion instructions. So, like was mentioned earlier, any position that we have that is taught, with the exception of position registers, has a user frame and a user tool or tool frame that are connected with that position, and it uses the information of those to decide where that point is relative to the robot. So anytime when creating a motion instruction, it's highly advisable to insert at the beginning of the program, or any time that these values would need to be changed, the user tool and the user frame that is used for the following set of positions, and which frames those positions were taught. This helps us to make sure that the values for both of those frames are the values in which were used to teach those positions. So to do that, we would go under our instructions key and going over to the next page or the next set of instructions, and there's this offset frames menu, and selecting that, we can either pick the user frame number or the user tool number, depending on which one we were wanting to select, and then we can select constant as a way to which will allow us to put a numeric value in for that user frame or that user tool. Okay, so now I'm going to do a demonstration on RoboGuide of some motion instructions, and then should set you up for your labs for chapter 12. So in this demonstration, I'm going to show you how to create a position register, and we can do that. We can access the position register file from two sources. We can either select this data button, or we can go through menu and go to the next screen, and then we've got data, and we can select position registers. So either way works. It's just whatever. If I hit data, then it just went to the register file, and I've got to hit F1, go down to position register. Okay, so either option is viable. Here in the position register screen, so we select this position register that we want to modify and record to. So here I'm going to select position register 1. I'm going to hit enter, and then I can enter in any kind of name that I want to call it. That seems like a great name. And I've got the robot in the position that I want to record to my position register. And so I'm going to go ahead and hit shift and then record. Now, if you notice that asterisk changed from an asterisk to an R for recorded. So now if I scroll over to the R, and I can now select the position, and it'll bring up the positional information for that robot. So the user frame and user tool are not defined under a position register. So the information that it pulled is relative to the user frame and user tool that was active at the time that the point was recorded, but it is not transferred over to the position register as that user frame and user tool. So this is just numerical information that can be applied to any user frame and user tool, but it may look different in the way that it's utilized by the robot. Here you can see that the configuration of the robot is transferred over, and so that's something that has to be consistent from one as we use the position register. Okay, so I'm going to, if I wanted to, I could go here and make some changes, direct entry changes, but I'm just going to leave it as is. So done. Okay, so now I can go ahead and create a program that then pulls in that position register. So let me go to my select menu. I'm going to filter for all my teach pendant programs, and let's go into the circle test. Okay, so at the very beginning, I'm going to insert a couple of different line items. So let me go to my edit command. I'm going to insert some lines. Let's insert 4 lines. And then here at the beginning, I want to include in my user frame and my user tool frame. So I'm going to go down to user frame and make sure that that is user frame 1. And then include my user tool as well. And we'll make that one also 1. Now, if I wanted to double check which user frame and tool frame these particular positions were taught in, I can highlight over that position number, select position, and then if I look up here at the top, I have the user frame and user tool that was used to teach that point. So now I'm going to go to done, and then here I'm going to enter in the position. I'm going to enter in a position register, so I'm going to just start as a position. Oop. And then come over here to my position number and then hit select choice. And now I can enter in a position register value. And so I'm going to hit 1. And as you can see, it brings in the comment along with it. So now I have an idea of what that point stands for, okay, or how it's used. So let's see how well this did in operating. So I'm going to go to step. Okay, and just to make sure it uses it all right, since it was already in that position, I'm going to go back up. Gets my little caution. I'm starting someplace different than where I left off. And there it goes back. And now we can use it to cycle through the program. Okay. Okay, the thing that I wanted to show in this program is the difference between different termination types, especially as we use continuous termination styles. So we have anything that we can use from 0 to 100%. 0 would be pretty much like a fine termination type. 100% is going to be the furthest away from that particular point, but will affect the speed of the robot the least. So in this program, I do a continuous termination type of 100, and then I also do a continuation type of 50, 25, and then I do another one at 100, but I slow my overall speed down to 25%. Okay, and so we'll look and see what the difference is between each of those. So first I'm going to do 100, then 50, then 25, then back up to 100, but with an overall speed of 25%. So let me make sure I turn this off. And now I'm going to go to my cycle start button so that it traces the end of arm tool path. And we'll see what that looks like. There's my jog move. There's 100. There's 50, 25. And then that middle, last one was continuous 100, but at 25%. See that there was a difference between the second to last one and that last path. So there can be a bit of a difference, so it's always a good idea to test. And this may not show up as well in a step mode, so doing a continuous test and then testing in auto and just bringing your speed way down.